Good day, everyone. Welcome to Chemistry with Professor John. All right, I hope you like thermochemistry. It's just about time, right? Thermo means heat, and just about time for summer. The That's heat energy. Now, first law of thermodynamics said we can't win, meaning whatever we do, the total energy is going to be the same. Okay, the because energy and matters are conserved. Okay, all right. Now, and if you translate that into formula, that would be whatever we do. The change in internal energy delta E will be equal to work and heat. Okay, they seem to go together. Every time you do work, you go out running, do some work, you feel the heat. Okay, that's the other products. Well, for gases, obviously, work is minus P times delta V. Okay, and P is external pressure and usually measured in ATM, volume in liters. So if you do a conversions, liter times ATM, that's about 101.3 joule. Okay, so we got time, we can derive those. Now, for us, when we run chemical reaction, heat is a big deal, right? One way to calculate heat is take the mass time C, which is heat capacity, and time delta T, which is the change in temperature. Okay, for example, how much heat must be added to a cast iron skillet with a mass of 524 gram to increase the temperature from 25 to 250 degrees Celsius? So obviously heat equal to mass times C. So now we don't know what C is, but we can look it up. Cast iron, it should be 0.48 joule per gram degree Celsius. That will be given. That's C. Mass, and then delta T will be 250 minus 25. That's delta T. Okay, so if you plug them all in, you should get everything cancel out except joule. Okay, so that's easy. And then you can try the other problem. This one is actually solved for C. So Q equal to mass times C delta T. So if you do the math, C will be heat. Make sure you convert it to joule divided by M delta T. So make sure. So in this case, it's 6,650 joule. Okay, divided by that. All right, now delta H is a really cool one. Here's another way to calculate heat of reactions. Heat of reaction we also call delta H, and delta H is minus heat of solution. So obviously it's going to be minus mass of solution times C times delta T of solution. All right. So I want to go over this example right here, number 3. So we got a solution, 100 mil plus 100 mil, that's 200 mil, and that's 200 gram, okay, of solution. Now heat is mass of solution times C 4.184 times delta T, which is 22 to 25. So that's going to give us heat. And because temperature goes up, so this one, we need a minus. Yep. Because this one is exothermic. Okay, so if you guys put in a calculator, you should get numbers. And then why do we have the molarity? Okay, and the volume, that if we want to do, if you take delta H divided by the number of mole, which is, that will give us joule per mole. And then you can also convert it to kilojoule per mole. Now the number of mole of HCl is equal to the number of mole of sodium hydroxide, and that's 100 ml and then 0.5 m, which is mole per liter. So that will give us 0.05. So if you take the delta H, you divide it by 0.05, you should get that kilojoule per mole. So that's if we want, to convert joule to kilojoule divided by 1,000. Okay. If we do a calorimetry, heat of reaction is going to be minus, don't forget the minus, solution plus the heat absorbed by the calorimeters. And here's a good example. Heat of solutions, so that would be 777. Some of you just do, like in the book they do 775, but I think it should be plus 3 gram time C delta T, and this is mainly water, so 4.184 time delta T, which is temperature go from 35.6 minus 23.8. So that's just the first part. And then the second part should be 893 joule per Celsius time delta T, which is 35.6 minus 23.8. Okay, and then when you add them up and convert it to kilojoule. Now this one we don't have to worry about mole, but we can divide it by the mole of glucose. If I ask for per mole, you can do that because you got the molar mass of glucose. So how do we know it's that many mole? That's 3.12 gram, 1 mole, 180.18. So that should be 0.0173 mole. And then all you have to do is just take minus 48.8 divided by 0.0173 mole, and that will give you the answer. Mole. All right. Now, if you remember in the class, we also mentioned about Hess's law. That's another way to calculate delta H. Okay, so we can calculate, after we calculate heat, which is Q, we can calculate delta H. But there's another way. We add up all the heat of formation of products minus heat of formation of reactants. And those numbers are given. So obviously this is the easiest way. calculate reactions. Given delta H of formation of reactant and product. That we don't have to memorize. And it's right here, Appendix G. If you go to Appendix G, you find all that, okay? Now notice the pure substance usually, not usually, always 0. This one I can't remember, but it's negative something. That's we look up in Appendix G. So for this one, it's so simple. Just take that minus the reactant side, which is 0. And that's the answer. All right. Okay, so you guys can work on the rest of them. That should be good for Chapter 5, you know. Pretty straightforward. Thank you, guys. I'll see you guys next for Chapter 6. All right.